In today's lesson, there are two things we're going to be learning. So first of all, we want to understand that an object of known luminosity in astronomy or cosmology is called a standard candle. So a standard candle is an astronomical object that we know the luminosity for. And secondly, we need to understand that standard candles can be used to determine astronomical distances. So, a standard candle is a class of astronomical objects whose luminosity is known. And by using this luminosity and the object's observed brightness or apparent brightness, and we also call this an object's radiant flux intensity, we can then use this formula here to start measuring cosmic distances to various astronomical objects. Now this formula is read like this. So we've got the radiant flux intensity on the left hand side is equal to an object's energy output, so its luminosity, which we measure in watts, divided by 4 pi multiplied by the distance from the observer to this object squared. So there are different types of standard candles that astronomers can use to measure distances. One type of standard candle you'll hear about quite often are stars known as type 1 Cepheids or type 1 Cepheid variables. Now, a Cepheid variable is a special type of star whose radius varies periodically. And when the star grows and shrinks, its apparent or observed brightness also varies. So if we were to pick one of these stars and measure its apparent magnitude over many days, weeks, or months, we can plot a graph that looks a bit like this. So we got apparent magnitude on the y-axis, and on the x-axis we got time in days. Now for this Cepheid variable, it has a period of 5 days, and it will quickly increase in brightness, and then it will slowly decrease its brightness over a period of 5 days. Now another property of Cepheid variables is all Cepheids of a given period have the same luminosity or power output. So if we were to measure two stars in separate parts of the sky, and these were type 1 Cepheid variables, and they both have a period in terms of its apparent magnitude of 5 days, both these Cepheid variable stars will have the same luminosity or power output in watts. And we can see this on this graph here, where we have the period of the brightness change on the x-axis now, at the bottom here, and on the y-axis we have the true luminosity output of that Cepheid variable. So we can see from this graph that Cepheid variables with larger periods or longer periods, in other words their change in brightness varies more slowly, these type 1 Cepheid variables have greater luminosities. But the smaller their period, the lower their luminosity is going to be. Now Earth-based telescopes can use Cepheid variables to measure distances of around or up to 13 million light years. But space-based telescopes can go up to 50 million light years. Now this isn't really that far compared to the known size of the universe, which is estimated to be around 93 billion light years across. But we're able to estimate the distances of galaxies surrounding our own Milky Way, so within the local group. So let's use this information now to answer a practice question. A Cepheid variable has a period of 10 days. Its radiant flux intensity, or its apparent brightness, as measured in Earth's orbit, is 1.4 times 10 to the minus 10 watts per meter squared. So use this graph now to estimate the Cepheid's luminosity, first of all, And then when we have the luminosity, let's try and estimate its distance from Earth. And the sun's luminosity is 3.9 times 10 to the 26 watts. Now, your answer for the luminosity might be slightly different to mine, but if we move vertically upward from the value of 10 days on the x-axis, I think this intersects this blue straight line here at about 3,000 times the luminosity of the sun, which is on the y-axis. So my estimate for the luminosity of this Cepheid variable, its true energy output, is 3,000 multiplied by 3.9 times 10 to the 26 watts. And to two significant figures, my answer is 1.2 times 10 to the 30 watts as the luminosity. So for part B, to measure the distance, we need to remember the formula for the radiant flux intensity. And the formula for the radiant flux intensity is the radiant flux intensity is equal to the luminosity of an object divided by 4 pi multiplied by the distance to that object from the observer squared. Multiplied both sides of the equation by the distance squared to isolate the distance, and then we square root both sides of the equation. Now the square root of 4 is 2, so I can move this outside the square root sign here. And we end up with this equation for the distance. So for the luminosity, I'm going to plug in my original calculated figure, which was 1.17 times 10 to the 30 watts. But I'm going to write this down here as 1.2 because we only know the accuracy of our figures by two significant figures. And then we divide this by the flux intensity that we've been given in our question, which is 1.4 times 10 to the minus 10 watts per meter squared. And we get a rather long answer, which again, I've rounded down to two significant figures. So 1.0 times 10 to the 20 meters in distance. But I'm going to keep the original value that I have on my calculator because we'll need that to calculate the next step. So the next step, we do have the distance now, but I'm going to convert this distance into light years. So a light year is the distance light travels in a single year. Now the speed of light to two significant figures is 3.0 times 10 to the 8 meters per second. And now we need to calculate the number of seconds within a year. So we got 365.25 days within a single year, multiplied by 24 hours in a day, multiplied by 60 minutes in an hour, multiplied by 60 seconds in an hour. And we get around 31 million seconds. And now to get the distance light travels in a single year, we multiply the speed of light by the number of seconds in a year. And you'll see that the units, the second part of the unit will cancel out here, leaving us with meters. So the distance light travels in a single year is 9.5 times 10 to the 15 meters. So to get the number of light years we got for our previous answer, we simply divide this distance by the distance of a single light year to give our distance in units of light years. So we do this and we get a value to two significant figures of 1.1 times 10 to the 4 light years. So about 11,000 light years. So to give a little bit of meaning to this distance, 11,000 light years is halfway between where the sun is in our Milky Way galaxy to the center of our galaxy. And our Milky Way galaxy is about 100,000 light years across.